Okay, this is example 1 in section 3.4, first section on optimization. Again, it's example 1, one that's actually in the book, but I wanted to go ahead and go through it because I think it's a pretty good example that shows you some of the interesting problems we can solve using these techniques. So let's go ahead and read the problem here. They say a manufacturer wants to design an open box that has a square base and a surface area of 108 square inches, as shown in the figure, which I've duplicated here. What dimensions will produce a box with maximum volume? Okay, so the box, they say, it has an open top and a square base. Okay, now normally a box has 3 dimensions: a length, a width, and a height. But when they tell us the base is square, they're just trying to make it a little bit easier for us. They say that they're basically telling us that the length and the width are the same. So we call that number x, which we don't know x yet. And of course the height can be anything else different, so that's what we call h. So what we'd like to do in this problem, if you read the second sentence, they want you to maximize the volume of the box. What's the formula for the volume of a box? It's length times width times height. Okay. Well, length is x, width is x, and height is h. So length times width times height is x squared times h. Okay. Length and width are both x. Okay, now normally if I asked you build the biggest box possible, x would be as big as you could make it and h would be as big as you could make it. But in the beginning of the problem, they give you some information that's going to kind of limit what x and h can be. Okay, they say the box here can only have a surface area of 108 square inches. Okay, so this is the primary equation. We want to maximize volume, but we've seen to do that we have to have volume just depend on one independent variable. So we need to either get rid of the h or the x and replace it with just the other variable. Okay. Well, that's where we have to get a secondary equation. Now, they tell us the surface area of this box is 108 square inches, and if you look in the problem, they'll give you this formula. This is the secondary equation: x squared plus 4xh equals 108. Okay. Where did that come from? Well, this box has 5 sides. Okay. It has a base. Okay, this bottom piece, which is x by x. So its area, the area of the base, is x times x, or x squared. Now it also has 4 sides, 4 walls, okay, of the box. And the area of each of those sides is x times h. Right? The area of a rectangle is just length times width, width times height. So this is x times h, this is x times h, this is x times h, etc. We have 4 of those pieces. So if I take the area of the base plus the area of all 4 sides, in total I need 108 square inches. Okay, that's what the surface area has to be. Okay, now if you look at this, I can solve this equation for one of the variables. And in fact, you could probably solve it for either one, but I think it's easier to solve it for h. And that's not too bad to do. All I do is I just subtract the x squared term over. I'll get 4xh equals 108 minus x squared. And then I'll divide both sides by 4x. So when I do that, I get h equals 108 minus x squared over 4x. Okay, so that's where the secondary equation is going to help me. It tells me that volume, even though it depends on x and h, through this secondary equation, I can write volume just in terms of x. You see, I can replace that h with this, 108 minus x squared over 4x. Okay. So now I've got a formula for volume that just depends on one variable, and that's key here. Okay, we can't maximize a function unless it just depends on one variable. So volume is now a function of just x. Okay. Now, before we go any further, we've got this formula for volume, depends on just one variable. We're about ready to start using calculus. But they always ask us to think about the domain, and again, this is mostly just to make sure that anything we come up with later on really makes sense in the problem. Okay, there is no domain given to us. But this is a real-world problem, and there might be some domain we can infer from that information. So x is the independent variable. Domain is asking us what can x be. Okay. Well, certainly x has to be bigger than or equal to 0. So 0 is less than or equal to x. Okay, why is that? Well, x is a physical measurement, and when you measure something, it has to be at least 0. Right? You don't have negative widths or negative heights or anything, so x has to be at least 0. Okay. Now, they also tell us, and again, this is something you kind of think about, some of the numbers given the problem, but they tell us that x has to be certainly less than or equal to the square root of 108. Now, where did that come from? Okay. Well, again, if you start thinking about how big x can be, certainly it can't be anything bigger than the square root of 108. Here's why. If x is the square root of 108, x times x, which is the area of the base, would be 108 already. And remember, the area of the whole box has to be 108 square inches, okay, the surface area of the entire box. So if x is the square root of 108, whatever that turns out to be, it's a little bigger than 10, like 10.4 or something, I don't know. But whatever that number turns out to be, that's the biggest x could be. Because if it's a square root of 108, we actually don't have anything left for the height of the box. Okay? So you could say that this is the valid domain of a problem. Okay?